program BSc, subject Mathematics, fourth semester, session number 15, topic evaluation of triple integral by change of variables. Myself Nagendra Padji. Last session we have discussed about evaluation of triple integral by change of variables. Change of variables using cylindrical polar coordinates. Cartesian to cylindrical. In this session, let us discuss about change of variables Cartesian to spherical polar coordinates. Spherical polar coordinates. What are the spherical polar coordinates? Let x, y, z be related to three variables rho, theta, phi by the relations x is equal to rho sin theta cos phi, y is equal to rho sin theta sin phi, z is equal to rho cos theta. That means in a triple integral, to change the Cartesian coordinates x, y, z, we should take the relations x is equal to rho sin theta cos phi, y is equal to rho sin theta sin phi, and z is equal to rho cos theta. So this Cartesian x, y, z into spherical coordinates we can denote it by rho theta phi. So Cartesian to spherical. To convert Cartesian to spherical, we should take x is equal to rho sin theta cos phi, y is equal to rho sin theta sin phi, z is equal to rho cos theta. The coordinates rho theta phi are called spherical polar coordinates of the point x, y, z. So to change this Cartesian to spherical coordinates, first we have to find out the Jacobian. What is Jacobian? Here x, y, z changes to rho theta phi. So Jacobian J is equal to dou of x, y, z by dou of rho theta phi. Dou of x, y, z by dou of rho theta phi. That is equal to determinant of dou x by dou r, dou x by dou theta, dou x by dou phi. First row, dou x by dou rho, dou x by dou theta, dou x by dou phi. Second row, dou y by dou r, dou y by dou theta, dou y by dou phi. Second row, dou y by dou r, dou y by dou theta, dou y by dou z. Dou phi. Similarly, third row, dou z by dou r, dou z by dou theta, dou z by dou phi. Okay, how we have to find out dou x by dou r, dou x by dou theta, dou x by dou phi. Here we have a relation x is equal to r sin theta cos phi. X is equal to rho sin theta cos phi. X is equal to rho sin theta cos phi. Differentiate partially with respect to rho, theta and phi to get a first row. When differentiating x is equal to rho sin theta cos phi partially with respect to rho, will get sin theta cos phi. Sin theta cos phi. When differentiating x is equal to rho sin theta cos phi partially with respect to theta, rho cos theta cos phi. Similarly, dou x by dou phi is equal to rho sin theta, differentiation of cos phi is minus sin phi. So minus rho sin theta sin phi. Similarly, differentiate y is equal to rho sin theta sin phi partially with respect to r theta phi. Y is equal to rho sin theta sin phi. Differentiating partially with respect to rho theta phi will get sin theta sin phi. Sin theta sin phi. Rho cos theta sin phi. Rho sin theta cos phi. When differentiating z is equal to rho cos theta partially with respect to rho theta phi, we will get cos theta minus rho sine theta 0. So after evaluating this determinant, we will get rho square sine theta. So when converting Cartesian to spherical polar coordinates, the Jacobian J is equal to rho square sine theta. Thus we have triple integral of f of xyz dx dy dz over R is equal to triple integral of phi of rho theta phi d rho d theta d phi. That means after taking x is equal to r rho sine theta cos phi, y is equal to rho sine theta sin phi, z is equal to rho cos theta, we will get a new function that is denoted by phi, new function in terms of rho theta phi. So that is denoted by phi of rho theta phi into Jacobian, that is rho square sine theta d rho d theta d phi. D is the region in which r theta phi vary as xyz or r. Phi of rho theta phi is equal to f of xyz. X is rho sine theta cos phi, y rho sine theta sin phi, z rho cos theta. Okay, let us take a problem. Evaluate triple integral of x plus y plus z dx dy dz, where R is the region in the first octant bounded by the sphere x square plus y square plus z square is equal to a square by changing it to spherical polar coordinates. If r theta phi are the spherical polar coordinates, then in the region r varies from 0 to a, theta varies from 0 to pi by 2, and phi varies from 0 to pi by 2. Thus, the given integral, triple integral of x plus y plus z dx dy dz is equal to integral of 0 to a, integral of 0 to pi by 2, integral of 0 to pi by 2, x r sin theta cos phi, y is r sin theta sin phi, z r cos theta, Jacobian r square sin theta, dx dy dz changes to d rho d theta dr d phi. Here instead of rho we have r, and dx dy dz changes to dr d phi d theta. So now first simplify this r sin theta cos phi plus r sin theta sin phi plus r cos theta. Here r is a common factor from these three terms, and if you take outside the integral r and Jacobian r square, we have r into r square, that is r cube, and multiply each term by sin theta. When multiplying sin theta cos phi into sin theta, that is sin square theta cos phi, sin theta sin phi into sin theta, sin square theta cos sin phi, and cos theta into sin theta. Here sin square theta cos phi plus sin square theta sin phi. Sin square theta is a common factor. Cos phi plus sin phi plus sin theta cos theta d phi dr d theta. Here r cube sin square theta sin phi minus cos phi plus sin theta cos theta, integrating with respect to phi first. The entire term is constant. Integration of d phi is phi. R cube sin square theta plus pi by 2 sin theta cos theta d theta dr. I integrate with respect to theta. Then integrating with respect to theta, r cube 2 into pi by 4 plus pi by 2 sin square theta by 2, limit 0 to pi by 2. integration of 0 to a r cube pi by 2 plus pi by 4. When apply the upper limit, sin pi by 2 is 1, that is pi by 1 by 2 whole square pi by 4 pi by into dr. Then integrate with respect to r. Pi by 2 plus pi by 4 after taking LCM, that is 3 by 4 into pi. Integrating with respect to r cube is r power 4 by 4, limit 0 to a. So 3 by 16 pi a cube. 3 by 16 pi a cube. A triple integral of r cube sin square theta cos phi plus sin phi plus sin theta cos theta d phi d theta dr. First integrate with respect to phi. When integrating with respect to phi, r cube sin square theta constant, integration of cos phi is minus sin phi plus integration of sin phi cos phi minus sin phi plus cos phi plus sin theta cos theta constant, integration of d phi phi. So that is r cube sin square theta minus cos phi plus sin phi can be written as sin phi minus cos phi plus sin theta cos theta into phi. Apply the limits 0 to pi by 2 for pi. Here r cube sin square theta sin pi by 2 1 minus cos pi by 2 0 for the upper limit. For the lower limit, sin 0 0 minus cos 0 1. So r cube into 2 sin square theta plus pi by 2 sin theta cos theta. After applying the upper limit for sin phi, cos phi and phi, that is r cube sin square theta sin phi pi by 2 1 minus cos pi by 2 0 minus cos 0 1 plus sin theta cos theta into phi by 2. So complete simplification. After taking the simplification, we will get r cube 2 sin square theta plus pi by 2 sin theta cos theta d theta. Now integrate with respect to theta. R cube constant 2 pi by 4 plus pi by 2 sin square theta by 2 pi by 2, limits 0 to pi by 2. So applying the upper limit, r cube 2 gets cancelled here, pi by 2 plus pi by 2 into upper limit pi by sin square pi by 2, that is sin square pi by 2 is 1 only, 1 square is 1, pi by 2 into 1 by 2 pi by 4, pi by 2 plus pi by 4 into r 3 by 4 pi dr. Integration of dr is r cube into dr, r power 4 by 4. So by taking the upper limit, 3 by 4 pi into a cube by 4, that is 3 by 16 a pi power 4.